All right, this lesson is our introduction to the idea of a function. The definition is written here for you. A function is a relation. Relation is just a set of ordered pairs, x's and y's, in which for each value of the first component, that's usually your x's, for each value of x, there is, the key word here is key phrase, exactly one. There is exactly one value of the second component. That's your y. Okay. I think sometimes the book may say the x is what's called the independent variable. And the y is the dependent variable, just to let you know. Okay, so for each x, there is exactly one y. The easier way to think of that is, what it really means is, in layman's terms here, no x value can repeat. That's really what it amounts to. No x value can repeat. Y values could, that's possible, but no x value can repeat. Let me give you some examples. It's an example right here. Let's take some ordered pairs. 2, 3, 5, 3, negative 1, 4. Okay. This is a relation. A relation is just a set of ordered pairs. The question is this a function or not? Now, for it to be a function, for each x value, there must be only exactly one y value. So when x is 2, y is 3. X is 5, y is 3. X is negative 1, y is 4. Did any x value repeat? No, they did not. All the x's were different, 2, 5, and negative 1. The y values did repeat, though. You'd have a 3 and a 3 here. That's okay, though. This, from the definition, does meet the requirements of a function. This is a function. It is a function. You may see these in what's called mapping notation as well. Here's where they put the x's and the y's in these little ovals. The x's are 2, 5, and negative 1, and the y's were 3 and 4. 3 and 4. And since 2, 3 is an ordered pair here, right there, when x is 2, y is 3, you would draw an arrow like that. When x is 5, y is 3, it would look like that. And when x is negative 1, y is 4, like that. And that's what that relation would look like in what's called mapping notation. It's still a function, though. Notice I have two different x values, the 2 and the 5, right there, and they're going to a single y value. That is okay. You just can't have an x value going to one single x value going to two different y values. Here's an example of that. Another one here. Let's take, for instance, the relation 2, 5, 1, 0, and 1, negative 2. Now, that is not a function because when x is 1, it actually has two different y values associated with it. When x is 1, well, y could be 0, or when x is 1, y could be negative 2. And so this is not a function. Not a function. Not a function. In mapping notation, it looks like this. Let's see, I'll put our x's in here, 2 and 1, or 1 and 2, doesn't matter. And our y's are 5, 0, and negative 2. Excuse me. And the 2 goes to the 5, the 1 goes to the 0, and the 1 goes to the negative 2. You see how I have right here, I have one x value, which is not going to exactly one y value. It's going to two different ones, and that is why it is not a function. Okay. Domain. All possible values of the independent variable, in other words, x. Range. All possible values of the dependent variable, that's your y. All possible values for y. So for this example up here, the one that is a function, it's very easy to identify the domain and the range. The domain for this one, put it right here. Oh, squeeze it in there, I guess. The domain is just your x values. And in this case, it would be right up here, the 2, the 5, and the -1. 2, 5, -1. The range, those are your y values, which were just 3, was twice, but don't write it twice, and a 4. 3 and 4 is the range. Okay, so domain is all possible values for x, and the range is all possible values for y. All right, moving on. Sometimes you have a graph and you want to know if it is a function. You can use what's called the vertical line test. Let me show you how that works. Let's say we have a graph that looks like, let's say, or like a parabola type shape there, like that. We want to know, is this the graph of a function or not? We apply the vertical line test, and what that means, without writing it all out here, is draw a vertical line wherever you like. Let's say I draw a vertical line there. It would only cross through the curve once, right there. If I draw a vertical line there, it only crosses once. No matter where I draw a vertical line, it will only cross one time. That means that we have a function. If we have something like this, then, if we were to apply the vertical line test here, what happens? It crossed through the curve more than once. It crossed through here and here. And since it did cross more than once, we would say that this is not a function. The reason the vertical line test works is because if you've drawn a vertical line and it crosses through the curve twice, let me just put some numbers to this as an example. Let's say this location here is -1, 2. Then this point down here has to be -1, something else. Let's say -5. And notice what you have. You have an x value that repeats. You have repeating x's, and you can't have that by the definition of a function. Here's another example. Just a line, linear function here. Obviously, it would pass a vertical line test. No matter where you draw a vertical line, it's only going to cross once. Function. As a matter of fact, all lines are functions except the ones that are perfectly vertical, but everything else would be a function. What about something like this? Well, right in this spot here, crosses more than once, therefore not a function. What if I give you an equation such as y equals 2x minus 1? Function or not a function? Well, if you were to graph it, and we know how to graph lines already, if we were to graph that, that's just a line that looks like that, and it would indeed pass the vertical line test, and so this is a function. A function. Okay, so that's how we use the vertical line test to tell if we have a function or not. Let's talk more about domain and range now. Let's take, I'll take another example like this, and then we'll complicate it a little afterwards. 3, 1, -2, 0, and 5, 0. Okay? Because no x values repeat, this is a function, and the domain domain is all possible values for x, and that would be the 3, the -2, and the 5. The range is the possible values for y. which would be the 1 and the 0, and the 0 again, but you don't write it twice in there. That's the domain and range. Well, what if I give you, instead of ordered pairs, what if I actually give you an equation such as y equals 2x minus 1? Well, what's the domain? And what are your x's? Well, your x can be anything you want it to be, right? We could plug in 2 in there for x if we feel like it. We could plug in 1. We could plug in -5. We could plug in fractions, decimals. It doesn't matter. We could plug in anything we want in there. This domain is all real numbers. That means all real numbers is the domain. The range would be 2. The range would be 2. Almost all the equations you deal with, the domain will most likely be all real numbers. The only time that it wouldn't would be if you had something like this. Let's say we had the equation y equals 1 over x minus 3. Can I plug in anything I want in there for x? Can x be 5? Yes. Can x be 4? Yes. Can x be 3? No, x cannot be 3 here because 3 would cause division by 0, and that's one of the things you can't do in the world of math. So x can be anything except 3. X cannot be 3. So here, for this equation, the domain is all x's, all real numbers, except 3. This is one way to write it. Here's another way. Excuse me. You could also write an interval notation like this. It's all real numbers except 3. That would be negative infinity to 3, 3 to infinity, union of the two sets. Notice that includes everything except 3. Another example would be something like this. Say we have y equals square root x. Well, we have learned, I think back from chapter 1, that we cannot take the square root. We can't take the square root of a negative number. And, well, we won't get a real number anyway if we do that. And so x here, for this equation to work, x must be greater than or equal to 0. And so here the domain is all x's as long as they are greater than or equal to 0. In the interval notation way of writing that, that would be bracket 0 to infinity. Now, let me do a couple more of these. Domain and range tend to be a difficult point for some students. Let's say we have the equation y equals square root x minus 4. What can x be? Can x be 5? Sure, x could be 5 because 5 minus 4 is 1. You could take its square root. Can x be 4? Yes, because that would give you 0 under there. Could x be 3? Nope, because if x was 3, 3 minus 4 is negative 1. You can't take the square root of negative 1 and get a real number. The x minus 4 here must be greater than or equal to 0. What's under the square root has to be positive. If you were to solve this inequality for x, you would get x needs to be greater than or equal to 4. That is your domain. Your domain is all x's as long as they're greater than or equal to 4. In our interval notation, that would be bracket 4 to infinity, just like that. Absolute value x. Can I plug in anything I want in there for x? I can plug in 0, I could plug in 1, I could plug in 3.5, I could plug in negative 2.4, it doesn't matter. I could plug any number in there that I want. I don't have to worry about taking a square root of a negative number. I don't have to worry about division by 0 here. The domain here is all real numbers. All real numbers. Okay. Now let's also consider the graphs of some of these. Let's sketch this one. Well, let me go to a new page here. Let's take y equals square root absolute value x again. If I make a sketch of this, we get a V-type shape, like that. You can get the domain and the range from the graph of the equation. Imagine you were to take the curve or the V here, and to pull it straight down onto the x-axis. If you pull it straight down on the x-axis, and keep in mind those arrows on the ends here, the entire x-axis would be covered. Since the entire x-axis is covered, that means that the domain, all possible values for x, the domain is all real numbers. Now, let me redraw it for you. If you take the curve, or the V here, this is the graph, and now you pull it onto the y-axis, pull it straight across onto the y-axis, like smashing it on the y-axis there this way. What part of the y-axis would be covered? Not all of it. It would only be covered from here and up. And that is why the range for this equation is not all real numbers. The range is y's are always 0 or larger. Y's are greater than or equal to 0 here. In our interval notation, that would be bracket 0 to infinity, like that. Okay, so you can get domain and range from a graph. Here's another example. Y equals 3x. Let's make a sketch. Y equals 3x we know is a line which looks something like this. Imagine we now pull this line onto the x-axis. And what I mean is pull this part down onto the x-axis, pull this part up to the x-axis. If I did that, the entire x-axis would be covered. And so the domain here is all real numbers. Now, instead of pulling the line onto the x-axis, what if instead we pulled it onto the y-axis, so smashed it this way and that way? If we smashed it on the y-axis, the entire y-axis would be covered, and that's why the range here is also all real numbers. And here's one more of this domain and range type problem. Let's say we have the graph a graph that looks like this. Let's say we have 1, 2, 3, and it does this, sort of a parabola type shape. There we go. Okay, we want the domain and the range for this graph. Imagine smashing this curve onto the x-axis, like this, and it does have arrows, so it keeps going, and this gets pulled up. This gets pulled down. If we were to smash it onto the x-axis, the entire x-axis would be covered. The domain is all real numbers. However, if we smash this parabola type shape onto the y-axis, smashing it onto the y-axis, the only part of the y-axis that would be covered, imagine pulling it this way and this way, the only part of the y-axis that would be covered would be from here, -3, and up. -3 and up. And that's why the range is our y's are always greater than or equal to -3 here. In our interval notation, that would be bracket -3 to infinity. Okay. So that's how you can get domain and range from the graph of a function. One other thing here, and that is function notation. Once you know that an equation is a function, you get to use function notation. The standard one is called f of x. This is said as f of x. It is not f times x. It's actually all one symbol. And it's just a fancy y. That's all it is. Now, in many books, you'll see it written like this, y equals that. Okay, it's just a symbol that you get to use instead of y. For example, we know that y equals 2x minus 1 is a function. It's a line. It passes a vertical line test. It's a function. Therefore, I could use function notation and write it that way. Instead of a y, we replace the y with an f of x. Now, one of the uses of function notation is to answer problems such as this. Suppose we want to evaluate f of 3. Here, let's do it this way. Well, if I want f of 3, let's put that up there. I need some extra room here. That means I replace the x with 3. So I'm going to take this equation, or this function. F of 3 would be 2 times x minus 1. The x is replaced with 3 like that. And so this works out to be 5. F of 3 equals 5. And really all that this means is when x is 3, y is 5. This really means that the line goes through the ordered pair 3, 5. That's all that it really means. Here's another example of that. Say we have g of x. You don't have to use f of x. G of x and h of x are their common function names. Let's say g of x equals x squared plus 1. Let's find g of negative 3, and we'll also find g of a. Okay. G of negative 3 would look like this. I'm going to replace the x in this original function up here with negative 3, like that. That goes right there. And if I work this out, that's going to be a positive 9 plus 1, 10. In other words, g of negative 3 equals 10. Remember, all that means is that this goes through the ordered pair, contains the ordered pairs of solution, negative 3, 10. Now, g of a. G of a means I replace the x with an a. So g of a equals a squared plus 1. And since I don't know what a is, I got to leave it like that. So g of a is a squared plus 1. If you want to write it as an ordered pair, it would mean when x is a, y is a squared plus 1. Okay, and that's function notation.